Light and sound seem instantaneous, but distant noise reveals that sound waves take longer to travel through air. Gravity dominates the everyday world, but gravity can be overcome. The physics of momentum can momentarily defy it. This is what we experience day to day, but beneath it all lie stranger worlds. Now, let's go smaller. We call this a mesoscale. Here, a tiny patch of skin seems like a vast landscape. Hairs rise from pores peppered with oil follicles and sweat glands. A variety of shapes also exists at peak complexity. Gravity is still very much present, but its force is overshadowed by friction and surface tension. For example, water at this scale holds together in a simple drop clinging in place. Its surface is simple and strong, like a thick gel. This microscopic forest is not unpopulated. Meet the Demodex mite. These tiny arachnids live unnoticed on the faces of perhaps 2/3 of humans. Physics are more gentle on such small creatures. A freefall ending in impact does no harm to such little mass. Sound at this scale can often have a dramatic physical effect due to acoustically induced vibrations. Now we move to the microscale. Within this thinnest thread-like capillary, we still observe a community of organisms, many of which are actually microcomponents that collectively form the individual human body. Here we see minuscule bacteriophage virus swarm and attack the bacterium. Everything is suspended in fluid, and gravity is irrelevant. The electromagnetic forces of chemical bonds and reactions is the strongest factor. Sound simply appears as large vibrations, purely a mechanical force. The predominant bobbing behavior of everything is called Brownian motion. It's characteristic of particles suspended in fluid. We have started to enter a more strange perspective at this scale, but as we go smaller, we'll get into the even more unfamiliar. The nanoscale. The inhabitants are a cast of molecular machines, DNA, proteins, carbohydrates. Linear molecules called lipids have the simple ability to repel or attract each other within fluid. They line up into sheets, bubbles, balls. Sound no longer registers as vibrations. The predominant force is electromagnetism. The geometry of molecules and the distribution of charges have huge effects on what properties they exhibit. Again, Brownian motion is a common factor. At this scale, only the faintest hint of a landscape remains. We've also lost all sense of individuality in these simple, almost robotic molecules. Going smaller, we reach the atomic scale. Here, we pass through electron orbital shells. Within, we find an arrangement of protons and neutrons forming a nucleus. Physics at this level is simply the group of electrons combined with nuclear forces. There is no sound at this level, since we are smaller than materials which could even convey vibrations. Generally speaking, patterns of geometry are spherical. We can go one step further. This is the subatomic scale. We are so small that we are catching a glimpse at the quarks inside the neutron. The strong force dominates attraction and repulsion. The weak force dictates how particles decay and shapeshift into each other. Electromagnetism is almost irrelevant here. Gravity is irrelevant. We are below the threshold of physics and shape. Behavior can seem random and even impossible by our normal physical rules. This is as far as we can go for now. Returning to our normal scale, we can look at everything a bit differently. We've explored how the unfamiliar chaos of the tiny weaves together to form our familiar world. Even the mountain is mostly empty space, throbbing with unpredictable particles held together by unfamiliar forces. Let's go beyond that. Let's go bigger. This is the scale of our solar system. Gravity is a dominant force controlling the shapes and arrangements of objects and systems. Smaller items like asteroids and planetoids can be oblong and irregular like objects on our normal scale. But in massive objects such as our sun, the planets and moons, gravity pulls matter toward a collective center. This produces spheres. We perceive no sound in the open spaces of our solar system since there is not enough matter there to transmit sound wave vibrations. However, if we dig into the particles of the icy rings of Saturn, one sounds might hear a direct contact with matter. We've also detected strange ticking patterns of waves from Comet 67P. They're possibly vibrations of charged particles of plasma streaming off its rocky surface. The solar system is spread out wide in a flattened disk shape of orbital paths and asteroid belts. Now let's accelerate out to the galactic scale. We lose sight of our sun in a cloud of millions of other stars. At this scale, matter is diffuse. Gravity is too weak to form spheres this large. Instead, galaxies are rotating disk shapes with denser centers. Distances are so vast, they are measured in a unit called light years. Although light seems instantaneous at our normal scale, it takes many years to travel between galaxies. Our closest neighbor, Canis Major dwarf galaxy, is 25,000 light years away. Some galaxies contain an active nucleus called a quasar, powered by a supermassive black hole. Their shape forms from massive jets of ionized matter. Distant galaxies are all slowly receding. A different force, dark energy, is stretching out to the fabric of space. We can go one step larger in our exploration. The cosmic scale. Here, the universe takes on a deceptive simplicity of a feathery cosmic web of up to 2 trillion galaxies. This is a battleground between gravity and dark energy. Gravity tries to keep matter together in tendrils of galactic superclusters, but dark energy is winning with a more powerful expansion of the fabric of space. If any sound can be interpreted here, it would be the hum of cosmic radiation. At this scale, light seems infinitely slow, and its slowness is marked by the spherical shape of the mass of tendrils. We perceive a sphere simply because observable light cannot travel fast enough to overtake dark energy expansion. This situation creates blindness approximately 47 billion light years in every direction. The rest of the universe is unobservable. This bubble is our cosmic horizon.